Tanks filled with liquid are common in industrial applications. Shown here, this is a draining fuel tank out of a car. Here's a leaking tank, also a fuel tank. So this one is being drained intentionally, and this one is leaking unintentionally. Here's a large storage tank, probably also actually storing fuel in here. And what these things all have in common is that they are these tanks that are filled with fluid, and the fluid is flowing out by gravity. And so you can imagine here you would turn that valve and the fluid would flow down that pipe. Here this fluid is draining out by gravity. And so this is what we want to simulate. And to do this, we're going to introduce a procedure where we use a mesh, that computational mesh that moves with the draining fluid. The geometry of our analysis will consist of this square region, 1 meter on a side. The upper surface will be a free surface, so this is where the fluid is exposed to air, and the fluid will drain out down here. So this will be a little region that where we'll set the pressure equal to 0. So the pressure here will be set equal to 0, and the pressure here will be equal to 0, or atmospheric pressure, and then we'll use a volume force here on this fluid to give it a unit weight, and that will be what drives the flow. In the second model that we'll look at, I'll also put a little rounded corner right down here. This is called a fillet, and this will help the computation of the moving mesh. So this is the configuration, and let's go ahead and take a look at how it's set up. So I'll show you how this works with two examples. This is called Moving Mesh Tank Drain Volume 2 Baseline. And we'll just go through the setup. There are no definitions and no global or local definitions in this model. It's quite simple. There's a square geometry and just 1 meter on a side, and then I put a point right here at this location. This will be the outflow point of the model. And so to run this, I use a Laminar two-phase flow moving mesh interface. And so I put that in, and this has really two components. It's got a Laminar Navier-Stokes solver, which is something that we've worked with before, and then it also has the physics that will allow us to set up this moving mesh. So the first four nodes here are defaults, and we want to just select the region with this free deformation. I think this is all overridden. All these conditions are overridden. The fluid properties, this is from before. This is the density and the viscosity, and so I'm just going to use the properties of water here. And initial values, we're going to give this fluid a unit weight, and so we'll be using gravity, and we'll want to assign an initial pressure. And so we'll assume that the pressure is just from the statics of the fluid weight, and so that will be that the pressure equals the depth times the unit weight of the water. So with our coordinate system, y is increasing upward. Here's the y coordinate. So 1 minus y, where that's 1, right there, that's the coordinate of the top of the model. And so 1 minus y is the depth, and then that's the density, and that's g. And so the product of those two is the unit weight. So the unit weight times the depth is what's used for the initial pressure. So we have an external fluid interface that we assign here, and we're going to have 0 pressure, and I'm just going to use the default surface tension. 7 e to the minus 4 Newton per meter. The outlet is down here, and we're going to assign it 0 pressure at that edge. And the other boundaries are these Neve slip boundaries, and I'm just using the default slip length here. Okay, so this is going to be important. This is going to allow the mesh to move, and we're going to move the mesh by having the top surface here of the mesh track the fluid interface. And so the way to do that is to use this condition where we prescribe the mesh velocity, and that's right here. If we go to moving mesh, we prescribe the mesh velocity, and we select this free surface. And what we're going to do here is use the mesh velocity like that. U is the velocity in the x direction, and nx is the normal vector. It's the vector in the x direction. It's the x component of the vector that is normal to this line here. And then this is the v is the velocity in the y direction, and ny is the component of the normal vector in the y direction. So when we take that product, that's the component of the velocity that is normal to the interface in the y direction. So we're going to specify this as the velocity, the n velocity, the normal velocity. So we have components of the normal velocity that are due to both u and v. Okay, so we set it up like that, and then we've got two more conditions, or one more boundary condition here, where we specify that the displacement normal to the boundary, the displacement of the mesh normal to the boundary is 0. So the mesh can move parallel to the boundary, but it can't move normal to the boundary. And then finally, we assign a volume force to the fluid that just is equal to the negative of the unit weight. So there's the gravitational acceleration, and that's the density. So that's the setup. The mesh itself is just the default mesh, and that's it. This study is really just the default configuration. The time is a little bit longer. The time is 10 seconds because we're going to open this up and the water's going to gush out and the water level will fall. So here's what it looks like. We're going to compute it, and this is the computation. We're viewing it as the analysis is running. You can see it's progressing like this. It gets about this far. This is the water right here. It gets about this far, and then you can see we're kind of stalled out at about 6.8 seconds. And if we look at the convergence plot, you can see that the reciprocal of the time step has dropped, and then it starts to increase, and now look at the takeoff. It's getting really big. Basically, when it gets big like this, it's 10 to the 7th. This model is very unlikely that this is going to converge. So at this point, the model is done, and you can see we're getting these kind of weird effects where the mesh is getting all distorted. And so what's happened here is the mesh has just gotten so distorted that the computations are not able to proceed accurately. And you can see these triangular elements that started out as roughly equilateral triangles, they're now very elongate. And so the accuracy is really poor with elements that are this distorted, and we're not able to converge. So this is done. This is all we're going to be able to do. And you can see these warnings about this inverted mesh element. That's probably over here where you see these highly distorted shapes. So that's the result. We were able to run it for about 6 seconds, and we got a lot of the water drained out. And let's take a look. Actually, so let me do this. Let me run it. If I stop it the way I did, then I can't really look at any of the results. But I'll show you another way to stop it so you can look at these results, even though we stopped it before it ended. If I go here to progress, and if I hit this button here, stop, then stop the execution. But now I can take a look at these values that were calculated. If I stop it using the little red X down here, then I can't look at anything. So we can take a look at the analysis, and if I go back here to the first time step, you can see that this is the region. It's started to drain a little bit, I guess. The way I'm plotting this is the velocity that I'm showing you, but this is probably how you're used to seeing it, as this color flood. And you can see the high velocity here where the fluid is flowing out. But what I'm doing is using wireframe, and this now is showing me the computational mesh. And if we were to zoom in there and we took these streamlines out, then we could see the colors that are on there. Let's just go ahead and do that. So yeah, there's the velocities that are on the mesh. But for this problem, I think it's convenient to be able to see the mesh, because we're interested in how the mesh is being distorted. I'm also interested in the streamlines during the flow, and so I have this turned on, and you can see as the tank drains out, we get the paths, and they're recalculated. It's kind of hard to see right now, but if we zoom in a little bit, you can see these red streamlines that are superimposed on the grid. So that allows us to learn a little bit more about just what's happening during this tank draining process. Okay, so we're progressing. We see how the mesh is being distorted, and this allows us to track the draining fluid. In this case, the water level doesn't really change much, so it's not all that interesting. But if you make this region longer and you do this, then it drops on this end and you get waves that slosh back and forth. And so it's pretty interesting in that scenario. But I just wanted to show a very simple scenario with these default conditions. So I'll leave it to you to set up scenarios that look more interesting. But the problem that we have here is that when we let this run, it crashes, and it crashes because the mesh becomes so distorted. So this problem of having the mesh become distorted is chronic with these kinds of moving mesh problems. If things move around by a lot, then you'll have this, and the analysis will end. And so what we can do to try to improve the analysis, or at least allow it to run longer, is to use a capability to automatically remesh the model. And that's shown in this other model called V2 Remesh. And this is very similar, except I've made a couple changes in the geometry. One, I made the outflow right here smaller, and I put this fillet. And these two elements of the geometry are essentially the same, except I moved the y-coordinate of that point down. And the fillet is it just puts a radius on the corner. And so I have a radius of 0.02 meters right here. It makes the corner rounded. And when I was setting this model up, what I found was that as the mesh was becoming distorted and was then when it was remeshing, there were some problems right down here in the corner. And so when I put a fillet in here, it seemed to improve that capability. So this is just a little thing to smooth out the remeshing. Okay, so let's take a look. I think all of this stuff is pretty much the same. The model is set up pretty much the same as it was previously. The difference, though, is if we go here to the study and we go to time dependent and study extensions, then I have checked automatic remeshing. And I'll show you what that does when we go and run this. Before we run the model, let's take a quick look at the mesh. This is the default mesh that we get when we put in the fillet. You can see the smaller elements down here where the geometry is curved. The small elements are put in to conform to that curvature. And down here we also have some smaller elements because the point that we put in is quite close to the corner, so the elements are made small right down here in order to conform to that geometry. So now when we run this, what I want to do first is not show you the remeshing. So I'm going to turn off the remeshing, and I just want to show you the basic analysis. And this will be with a moving mesh, but without the remeshing. And so let's see. Actually, I'm going to stop it and I'm going to switch over. Okay, what I've got to do here is turn to that plot, and now I can see the plot as it runs. Okay, so here's the mesh, and once this starts running, then it starts to deform and compress, and it goes down like so, and actually it does really a remarkable job. But the problem is that these elements are so distorted that we're concerned about the accuracy. We'd have some problems, or we definitely have some cause for concern about the accuracy, and you can see that we've gotten some problems with convergence. This convergent plot is just really going up off the charts, and so that's not a good sign for this analysis. So I'm going to stop it here, and we're going to then go to the automatic remeshing. But before we do that, what I want to do is point out this change that I made. In the previous model, I had the boundaries be zero normal mesh displacement. So all of these boundaries, I said that the mesh displacement was going to be zero. And that worked okay for the model that we had, but it doesn't work okay when we're doing remeshing. We'll have some problems. And so instead of requiring that the displacement is zero, what I did was to require that the velocity is zero. So the rate of change of the displacement. So all of these boundaries here have the boundary on the mesh is that the velocity is equal to zero. So what we need to keep in mind is when we set this problem up that all of the boundaries have to have a condition for the mesh and for the fluid flow. So all of these boundaries are zero normal mesh velocity, and this upper boundary is the prescribed velocity based on the fluid velocity. We also have this external fluid interface, but that's not, well, we're using both of these to set up the boundary condition on the upper boundary. Okay, so now we're ready to run this with automatic remeshing. We're going to check automatic remeshing there. And I know, because I ran this earlier, that I'm going to get a plot and plot group 4. So I'm going to switch that so I can watch it as we solve it. So here's the run. There's the mesh, and it'll start up here in a second. It goes, and now there it remeshed for the first time. And so we have a new mesh, and we have a crash. Okay, so the good news is we got the remeshing to go, but the bad news is that it only ran to 16 seconds and stopped. So there are some settings here in the automatic remeshing that may help. If we go here to automatic remeshing under the study and use consistent initialization, then that is something that may help with the remeshing. So we'll try that. So we have our initial mesh and we run it. It goes pretty quickly to 16 seconds. It remeshes and now it keeps going. Now 36 seconds and it remeshes. What's happening is running, the elements are becoming distorted, and then when it gets to be a certain amount of distortion, it redoes the mesh, and we get an analysis that runs out to 100 seconds. And so that was the full duration of the analysis, and you can see this is what the mesh looks like when we're done. We've got some small elements right here at the curve part of the domain. Here in the main part of the domain, the elements are quite large. And so if we go back to the meshes here and open up this node to take a look at some of these deformed meshes, you can see that the simulation has created 5 deformed meshes. So it was remeshed 5 different times. Here, this is mesh number 3. And one of the things that really strikes us is that this mesh has fairly equidimensional elements. And that's going to be important because the equidimensional elements will allow the solution to be more accurate than when the elements are highly elongate. And we can take a look at this, basically a measure of what's called the mesh quality. And there are various different things here, statistics about the mesh, and the average element quality, minimum quality are given here. So the average is 0.94 and minimum is 0.82. Those meshes with the highly elongate elements have mesh qualities down at about 0.2. And in fact, when we set up this remeshing capability, let's go here, the automatic remeshing. See here the minimum mesh quality. What happens is the elements become elongate, the mesh quality goes down, and when the minimum quality reaches 0.2, then that's what triggers a remesh. And so we can change that if we like, and that there may be cause for that if we were trying to tune the remeshing capability. But that mesh quality is the same term that we can take a look at here under statistics. And we see that for this mesh that's been created, the minimum element quality is 0.82. 1 is the maximum, and so this is a pretty good quality mesh.